Welcome to this explainer. Today we're going to dive straight into the literal nuts and bolts, or I guess paper and solvent, of chromatography. If you've ever wondered how scientists actually unmask the hidden components of complex mixtures using nothing but a piece of paper, some liquid, and incredibly basic math, well, you are in the perfect place.
Here's our roadmap for the breakdown today. We'll start with setting up the experiment, tackle 3 crucial questions about that setup, measure the solvent run, and finally, calculate the RF value.
All right, part 1, setting up the experiment.
So you want to set up a chromatogram. We've got 3 absolutely crucial physical steps to get this right. First, you grab your chromatography paper and draw a perfectly straight baseline with a pencil, exactly 1 centimeter from the bottom edge. Next up, you apply your sample. You just take a tiny spot of the mixture you're testing, say a mystery ink or dye, and drop it right on that baseline using a dropper or a capillary tube. And finally, you gently lower that paper into a beaker of solvent. The trick here, you gotta make sure that pencil baseline is hovering just slightly above the liquid level.
Moving right along to part 2, the 3 crucial questions.
You know, in a lab setting, literally nothing is done by accident. So here's a fun little puzzle for you. Why on earth do we insist on using a standard graphite pencil for that baseline instead of just grabbing a regular pen? It seems like a totally minor detail, right? But it actually makes all the difference.
Here's the deal. If you were to use a pen, the ink from that pen could literally dissolve straight into the solvent the second the liquid touches it. That pen ink would just travel right up the paper alongside your actual sample, and boom, your entire chromatography is ruined because your starting line just crashed the experiment. A pencil, on the other hand, graphite doesn't dissolve in the solvent. It stays perfectly put, which keeps your baseline totally intact so you can actually trust your measurements later on.
Okay, puzzle number 2. Why are we so incredibly obsessive about keeping the solvent level strictly below that pencil baseline and our mixture spot?
Well, think about it. If that liquid touches your spot directly, the ink coloring is just going to dissolve straight into the pool of solvent at the bottom of the beaker. You'll lose your sample instantly, just completely washed away. For this to actually work, the solvent has to creep up through the paper and carry the spot with it, rather than just swallowing it up at the starting line.
And that brings us to the final question of our setup phase. Why do we bother covering the beaker? Once that paper is in, we usually pop a lid or maybe a watch glass right over the top.
That simple lid is actually doing 2 huge things for us. First, it completely saturates the air inside the beaker with solvent vapors, which guarantees a much more effective, clean separation. And second, it literally just stops your solvent from evaporating out into the room. Pretty straightforward, but absolutely essential.
All right, on to part 3, measuring the solvent run.
Now, once this starts, you really gotta watch the process like a hawk. When that creeping solvent gets to about 1 centimeter from the very top of the paper, it is time for immediate action. You pull that paper straight out of the beaker. Then, and you have to be quick about this before it dries, you grab your pencil again and draw a brand new line across the paper to mark exactly where the solvent reached. That marks your finish line.
Which brings us to part 4, calculating the RF value.
This right here is the mathematical climax of the whole explainer. To actually quantify what just happened, we use something called the RF, or retention factor value. By definition, finding the RF value just means figuring out the ratio between 2 things. The maximum distance covered by an individual component, like a specific dye that's separated out, divided by the maximum distance covered by the solvent itself. And that maximum distance the solvent traveled, that second pencil line we just drew, we call that the solvent front. Let's put some real numbers to this, because the math is beautifully simple. Imagine taking a regular ruler and laying it right next to your chromatogram. Let's say you measure from your bottom starting baseline up to that top pencil line, your solvent front, and it's exactly 10 centimeters. Okay, easy enough. Now look at one of the separated spots on the paper. We'll call it component A. You measure from the baseline up to component A, and let's say it traveled exactly 2.5 centimeters. All you do now is set up a super simple division equation, 2.5 divided by 10. Do that quick math, and you get an RF value of precisely 0.25 for component A. Now, why does that actually matter? Because that number is essentially a unique mathematical fingerprint for that specific component under these specific conditions. Every distinct component hiding inside your original mixture is going to travel its own individual distance, which means it gets its own individual RF value.
So as we wrap up this explainer, I want you to really think about this. We started with nothing but a blank piece of paper and a single mystery spot of ink. But by just controlling how a liquid moves and using some basic division, We unlocked a standardized, repeatable ratio. How wild is it that measuring just a few centimeters on a simple strip of paper empowers scientists all over the world to completely unmask the hidden identities of totally unknown chemical mixtures?